Hi. Geologists have known for over 100 years that plates move around the Earth's surface. Wegener's geological evidence of continental drift showed us that the continents must move. It wasn't until much later, though, that geologists like Hess or Tuzo-Wilson, working on ocean basins, really got to grips with the mechanism. What actually made the continents move round? We saw that the evidence for that must be in the oceans, with the idea of seafloor spreading. We can sort of see a small example of that here in Iceland. But this still begs the question, why are the plates actually moving? We know that they move. What is it that makes them go? Now, there are a couple of theories. This is the conventional model that Tuzo-Wilson came up with in terms of divergent plate margins creating new oceanic crust, which then gets destroyed at subduction zones. And you can see on this diagram this concept of a convection cell within the mantle that would drive this movement. It's an interesting idea, and it's one that does fit in with parts of the evidence, particularly in terms of heat flow that we find concentrated at convergent margins where we have a higher heat flow, and at its lowest at subduction zones. But there are some issues with it. Let's have a look. Let me show you a video that illustrates this model, that animates it a little bit more. And let Ian Stewart explain a little bit more about it.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart, and it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
So, this idea of the mantle plume, which we can see animated in this GIF here, of this concentrated heat rising up through the mantle, hitting the base of the lithosphere and mushrooming out. We can see here in a thermal profile, concentrates heat and perhaps explains where we get this movement from. Even the solid mantle we can explain away through different timescales of movement. You know, the short period of time that an earthquake passes through where the mantle behaves as a solid, or the longer period of time as this heat is moving slowly where it can flow, it can become ductile. Now, these mantle plumes do fit a lot of the evidence that we see, particularly in terms of heat distribution. We think there are several of these around the Earth. This is a 3D model showing, if you like, the Earth with most of the mantle removed. But it's not universally accepted. There's a website called mantleplumes.org, which is run by a group of geologists who are sceptical about the whole concept of mantle plumes. Go and have a look at the website, but if you don't enjoy your geology to be argumentative or contradictory, I wouldn't look at it. So if mantle plumes exist, what we should be able to do is trace this heat signature through the mantle. You're looking at cross-sections through the mantle. These are in 3 different directions, all going through the same place. This is a place called Afar in Ethiopia. It's in the East African Rift, so it's a divergent plate margin, and it uses a technique we call seismic tomography. Slices through the mantle, looking at the behaviour of earthquake waves. And we can use that to reconstruct temperatures. The hotter colours here represent the higher temperatures. If we look at this particular piece of data, we can see that there's evidence of a heat trace running from the outer core mantle boundary right the way up to the base of the lithosphere. So perhaps from this we can interpret that underneath Afar, a mantle plume will exist. However, if we look at other areas where we'd expect to find a mantle plume, like this is Hawaii. Now, if you look at the data underneath Hawaii, we can see, again, we have a trace of heat coming from the base of the mantle up to its top, but it's not quite as continuous as we see under Afar. Does that mean we have 2 lots of convection cells operating within the mantle here? It perhaps starts to sow a seed of doubt. What's even more unusual is if we look underneath Iceland. The data underneath Iceland doesn't show a continuous pattern of heat. What we see underneath Iceland is a concentration of heat in the upper mantle. Now, is this just a result of a reduction in pressure? Or is this a result of the type of convection we might see in a lava lamp, if you like, where we get blobs of heat rising rather than a continuous stream? Clearly, there's a lot more to understand about this. Increasingly, geologists are turning to another model. This is an idea we call Slabpole. Now, to understand Slabpole, we must get to grips with the densities of the materials involved here. Now, we know from our practical that continental crust has a density of about 2.7. Oceanic crust is denser, 2.9. Explains why it sits lower on the Earth's surface. And we know that the mantle in the asthenosphere has density of about 3.2. It helps us explain how, or the position that these different parts of the Earth actually sit on the surface. Now, the idea of Slabpole is that the subducting plate pulls the rest of the oceanic crust with it. And it relates to, or it relies on, the idea of what we call an eclogite. Now, an eclogite is a metamorphic rock. It's not one we've come across before, and it's not one you need to identify. But an eclogite is where we have a oceanic crust that has had the water taken out of it, that has perhaps some of the more silicic minerals melted out of it. And what we see is a density as a result of 3.5. Crucially, denser than the lithosphere. So if we've got a denser material in that subducting plate, that's going to be dragging it down into the mantle. It's going to be sinking within the mantle, pulling the rest of the crust behind it. It's a simple but effective idea. However, although it can explain perhaps the movement of for example, the Pacific plate, what about the Eurasian plate, the one we're on? We know it's moving, we can measure its movement, yet we don't have a subduction zone. There's no part of the Eurasian plate that's actually being subducted. So why is that moving? It's a fascinating topic. So, as we look at Erta Ale, a lava lake in Afar, right on the divergent margin here, possibly the surface expression of one of these mantle plumes, and we think about our conclusions, although in English perhaps rather than Aramaic. It's a fascinating topic, one that is still, I think, unresolved. Do we have a combination of both of these processes actually influencing plate movement? Or is it simply a case of Slabpole being the dominant one and that's moving the other plates around? I think we need to understand a lot more about how the mantle actually works, the whole process of mantle dynamics, if we're really going to get to grips with this and come up with a definitive answer. Both techniques are on your both theories are on your specification. What do you think? What do you think is the most likely explanation? Come up with some interesting questions and ask me when I see you. I'll see you then.